Okay, so the last topic from 4.5 is how we deal with definite integrals. And there's some things we've got to be careful of here because a definite integral is measuring not an antiderivative, it's not a function. It wants to know the net area between a curve and the x-axis. And when I say net, I mean positive and negative area makes sense. This is usually called signed area. So when I'm computing with definite integrals, I have to be careful that when I do my substitution, I substitute everything. Okay? And so that's going to show up in the theorem that describes substitution for definite integrals. So that looks like this. If I have an integral, a dx integral from x equals a to x equals b, and I recognize it as resulting from taking a derivative of a composition. That is to say, if I'm looking at f of g of x, g prime of x dx, if it has the form that we're looking for when we do substitution, when I make the substitution, I have to change every single x-type thing into a u-type thing. What I mean by that is the limits of integration are also x values. The limits of integration are x values. So they have to change too when I do a substitution. If I make the substitution u is equal to g of x, that is, I'm going to replace u or g of x with u, every value of x has to be replaced with a value of u. This turns into the integral from u equals g of a to u equals g of b of f of u du. The limits change. Okay? If I start with x values for my limits, I have to plug them into the substitution to figure out what the corresponding u values are. Now, the beautiful thing about this is that it doesn't change the area under the curve. The area underneath this curve in the original setup with the x functions is equal to the area under this curve with the u variables. So once I do one substitution, I actually don't have to substitute back anymore because this isn't asking for a function, it's asking for an area. So as an example, let's walk through a couple of functions where we change limits of integration. Okay. So how about the integral from 1 to 2 of dx over 3 minus 5x squared. Okay. Now, this is an x integral. I recognize that I don't know this is a table integral because it's clearly a composition, and so I'm going to try substitution. So I'm going to try the substitution. U is equal to 3 minus 5x. The reason that I choose 3 minus 5x instead of something like 3 minus 5x squared is I think of 3 minus 5x as the most complicated expression sitting inside the function 1 over x squared. Okay? So I'm going to try the substitution first, and I'm hoping that it's going to give me an integral that I can actually write down the antiderivative for. I know that I'm going to need du is equal to minus 5 dx. And because I'm changing variables from x to u, I'm also going to have to compute, well, x is equal to 1 is going to turn into u is equal to 3 minus 5 times 1. I have to plug the x values into the substitution to figure out what the corresponding u values are. What I'm saying here is that whenever x is equal to 1, u must be equal to negative 2. Whenever x is equal to 2, that means that the u value that went along with that must be negative 7. So I'm going to just wholesale transform this function in this way. I guess there's one thing I forgot to do here, which is I also want dx, so I can make that substitution as well. So if du is equal to minus 5 dx, then dx is equal to minus 1/5 du. Okay, so after substitution, this integral is going to be Well, the 1 that was here in the x integral is going to get replaced with the -2 that's here in the u integral. The 2 that's here in the x integral is going to get replaced with the -7 that's here. Dx gets replaced with -1/5 du. And 3 minus 5x squared is u squared. So now I can just do some algebra to simplify this before I get started. I'm going to pop the -1/5 out front. And then using the negative in front of the 1/5, I can actually reverse the order of the limits of integration. And now I can just compute. So the integral of u squared is -1 over u. This is just by the power rule. The integral of u to the -2 is equal to u to the -1 divided by -1. So this is equal to 1/5 of -1 over u evaluated from -7 to -2. If you plug those in and you do the computation, once you do the fraction subtraction, what you end up with here is 1/14. Now, do you have to substitute back? This is where you have to decide, have you finished answering the question? Well, what is this asking for? It's a definite integral, so it's asking for area. This is an area. So because this is an area, as long as I've gotten an area down at the bottom, I'm finished. I don't need to substitute back because there's nothing to substitute back into. Some of you may have learned a method where you compute the indefinite integral first, then you substitute back and you plug in the original x values. That's fine if you learned it that way, but often that's a significantly slower and more mistake-prone method than just transforming everything all at once and computing the same area from the u integral instead of trying to transform it back into some kind of x expression. Okay, so another example. This is example 5. So we're going to look at the integral from 1 to 5 of the square root of 2x minus 1 dx. I'm going to try, now I already know that I've done this integral with substitution in the indefinite section, so I could do it that way and then figure out the antiderivative and plug in, but I'm going to try to stick consistently with the idea that when I compute these things, I want to transform everything with no transformation back. I'm going to take this area integral and I'm going to turn it into another area integral in u variable. And when I compute the area, I'll just be done with the computation. So just like before, I'm going to identify my u value. So here I see a 2x minus 1 living inside of a square root. So u should be equal to 2x minus 1. I'm going to compute du is equal to 2x dx. And so du over 2 is equal to dx. There's my dx substitution. And I have one last thing I need to get rid of, which is these values right here, the 1 and the 5. So to get rid of the 1 and the 5, I'm going to have to take those x values and I'm going to plug them into the expression for u to figure out what the corresponding u values are. So if x is equal to 1, then u that corresponds to that is 2 times 1 minus 1, which is 1. And if x is equal to 5, then the corresponding u value that goes along with that is 2 times 5 minus 1, which is 9. Now I'm ready to transform every piece of this integral. And so I end up with, well, the 1 transforms into a 1, and the 5 transforms into a 9, and the 2x minus 1 is just a u, and dx is going to get turned into du over 2. Before I actually do the computation, I can pull the 1/2 out front. And I'm going to write the square root of u not as root u, but as u to the 1/2, because I need to have a fractional exponent in order to use the power rule. After you do the computation here, you should find that this is 1/2 u to the 3/2 divided by 3/2 evaluated from 1 to 9. And you plug in and you compute with the fractions. What you're going to end up with is 130. 26 over 3. 130 nothing. I don't know. So I want to add here that if you have trouble with the fractional computations, please reach out and we can go through how to approach sort of the algebra, the numerical algebra down at the bottom of this. I want to emphasize again here that there's a lot of places where your knowledge, any gaps in your knowledge are going to show up. If you came out of a high school calculus class and you skipped over calculus 1 and you're starting and this is your first class in college in mathematics, I want to make sure that when we get to problems like this, that expect that you know how to compute things like this, that you have memorized the idea of taking the power rule of u, and you didn't do that in your calculus class in high school, or it's been so long since everything shut down in March that you never learned this because it was supposed to be at the end of the course, or you learned it but it's been 6 months and you forgot everything. When you get to steps like this, if I do something where I jump from an integral to an antiderivative and you don't know how I got there, please make sure that you send me an email or show up in office hours so that we can talk about it. There's going to be lots of stuff like this that happens over the semester. Calculus 2 is hard enough on its own without having to fight knowledge that you were supposed to have, but that maybe, a global pandemic got in the way of you actually picking up. Okay, so that concludes examples 4 and 5 of working with definite integrals. At this point, what you should do is you should go and start working through the homework exercises. Anything that you hit that you have questions on, you should either post in the discussion room, you should come to my office hours and we can talk about. I'm willing to compute the answers to any single question. I would much prefer if when you come to me with a question that you come with your efforts to try to do the question on your own first. You're going to get a lot more out of this class if you do it that way. All right, so hopefully this was a reasonable introduction to how this is going to go. If you have suggestions for things that would make this easier to digest, let me know. And because I've thought a lot about how to do this class, but I'm also learning myself about the best way to approach mathematics in a Zoom type environment. You can feel free to check the Canvas page for the PowerPoint that I produced in the course of doing these notes. And this is the way this is going to look as the semester goes on. So have a good time doing your math.